Today we're going to learn about standard form to scientific notation. What is standard form? Standard form is the way we normally see a number written. For example, 83 million. Scientific notation is a shorter way to write very large or very small numbers. For example, I can change 83 million to 8 3/10 times 10 to the 7th power. I'm going to show you how to do this. Let's get real. I mean, who really uses scientific notation? Well, here is a germ, and doctors, marine biologists, scientists would all use scientific notation, maybe to write the diameter of a germ in without using all the zeros that they would normally have to write out every single time. Astronauts in NASA would use scientific notation to write the distance from the Earth to the Sun, so that they wouldn't have to write out all of those zeros every single time that they write that number. Let's start with taking a very large number and writing it into scientific notation. Here's the Earth and here's the Sun. The distance between the Earth and the Sun is 93 million miles. Okay? So let's take these steps. These are the steps that we're going to use to change a very large number and write it into scientific notation. First step says move the decimal point so there is only one non-zero digit to the left. So here's 93 million, and I want to move the decimal point. I know that there's a decimal point at the end of this number. So I'm going to move it until there is only one non-zero digit in front of the decimal point. Now, so I'm going to move it all the way down so there's only a 9 in front of the decimal point. So my new number is going to look like this. 9, decimal point, 3, and then I could write out all those zeros behind it, or in scientific notation, I'm not going to write those zeros out, okay? Let's get to step 2. Count the number of places the decimal point would need to move to get to the original number. Well, how far would I have to move this decimal point to get that number right there? Well, let's check it out. 1, 2, 3, 4, 5, 6, 7. I'd have to move it 7 places to get back to the original number. So, since the decimal moved to the right to get the original number, I'm going to write my exponent as a positive. Okay, so I have 9.3 times, and it's always going to be times 10 because we're adding zeros onto the number. Times 10, and how many times did we move the decimal point? We moved it 7 times to get the original number. Okay, so times 10 to the 7th power, and we moved it in positive direction. We moved to the right. Remember, right on a number line is positive, left on a number line is negative. So since we moved our decimal point to the right to get to the original number, we have to have a positive exponent. Now let's take a very small number and write it in scientific notation. Let's take the diameter of DNA. Okay? This is how we would normally write the diameter of DNA. Now, if you're a scientist, you don't want to write this every time. Okay? Now, step 1, we're going to move the decimal point so there's only one non-zero digit to the left. Hey, that's the same as it was in changing a very large number into scientific notation. So we are going to move the decimal point so there's only one number in front of it. Well, how far down would I have to move the decimal point so there's another number besides 0 in front of it? I have to move it all the way behind that 2. So I'm going to rewrite this 2. I can put a point there if I want to, just to show you, but it's just a 2. And how many places did it move? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so next, we're going to count the number of places the decimal point would need to move to get to the original number. So here's my new number. how many times would I have to move the decimal point to get back to this number? 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd have to move it 9 times to get back to the original number. Okay, so I'm going to put times 10. I'm going to put to the 9th here because I had to move the decimal 9 times. But the last step, since the decimal moved left, your exponent is negative. Okay, pay attention to that. Your exponent's going to be negative. Since when I went to change it back to its original number, I moved the decimal left. Left on a number line is negative. Okay, it's a negative direction. So my exponent's going to be negative. Now when you have a decimal number, your exponent is going to end up coming out to be a negative number. When you have a whole number, you're going to have a positive exponent. All right, so let's practice this. Practice examples. 55 is this billion, 300 million. Well, I don't want to write that number out every time if I have to do it a lot. So let's change it. Okay, I remember I have to move my decimal point so that there's only one number in front of it. So it was here. I'm going to move it all the way to here so that only the 5 is in front of the decimal point. I'm going to write out the other numbers that are left. Okay, and everything with a 0 I'm going to represent with times 10. Now, how far would I have to move this decimal to get the original number? Well, if it was here, which is where I moved it to, I'd have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Times 10 to the 10th power. Okay, number 2. Number 2 is a decimal number, and I'm looking to put one digit, one non-zero digit in front of the decimal. So I'm just going to move that decimal all the way over here. Okay, between the 2 and the 3. I'm going to rewrite my new number, 2.34, okay, and I'm going to write times 10, okay, because at this point now we're counting zeros, or places. We're figuring out how many places we need to move that decimal to get back to the original number. So 1, 2, 3, 4, 5 times 10 to the 5th power. And which direction did I have to move the decimal to get back to my original number? I moved it to the left. To the left on a number line are negative numbers, so this is a negative 5. Number 3, 8,700,000. Let me write this in scientific notation by putting a decimal behind one non-zero digit. So I'm going to put it behind the 8, 8.7. I'm right times 10. Okay. So if I had the decimal right here, how many places would I have to move it to get back to the original number? 1, 2, 3, 4, 5, 6. 6 places, so times 10 to the 6th power. Number 4, I have another decimal number here. I'm going to put my decimal behind the first non-zero digit, and if I put it here, how many places will I have to move it to get back to the original number? 1, 2, 3, 4, 5, 6, 7, 8, 9. So times 10, 10 to the 9th power. Which direction did I move the decimal? I moved it in a negative direction, so it's a negative 9. Pause it. I want you to pause the video right here, and I want you to go ahead and try these out. Okay, 28,000. I am going to write 28,000. Pause it. I want you to go ahead and pause the video right here, and I want you to try out number 1, 2, and 3 on your own, writing number 1 and 2 in scientific notation and answering the question for number 3. Okay, 28,000 written in scientific notation would look like this. 2.8 times 10, and how many places would I have to move it to get back to the original number? 1, 2, 3, 4. To the 4th power. Number 2. I'm going to move my decimal behind the first 9 zero digits, so that would be the 1. 1.302 times 10 to the, well, how many places would I have to move this decimal to get back to the original number? 1, 2, 3, 4, 5. So it's to the 5th power. And which direction did I move the decimal? I moved it in a negative direction, to the left. So that's a -5. How do you determine whether to use a positive or negative exponent when using scientific notation? Okay, the answer to that would be if you move the decimal in a positive direction to the right to get your original number, then you use a positive exponent. If you move the decimal to the left to get your original number, then you use a negative exponent because negative numbers are to the left on a number line.